Welcome to another Data Science Deep Dive on our technical track. In the following session, Gerald Fahner, Senior Principal Scientist at FICO, shares how FICO combines machine learning with modern segmented scorecard technology and domain expertise to maximize predictive power of the FICO score while adhering to explainability and regulatory requirements. Enjoy.
I hope it's a home play. I work for FICO in Austin. And speaker before me, Namita, just mentioned the importance of explainability in AI. Obviously, this is more and more of a concern that we're building too many black boxes and learning biases and potentially suffering garbage in, garbage out situations. So it's probably no more than in credit scoring, where the eyes of all people are on credit scoring. And as they sometimes say, the FICO score is probably the most scrutinized model in the world. So when we try to apply the latest and greatest machine learning and AI techniques, we need to be especially careful that remains explainable. But first, a few words about FICO. So FICO has been a pioneer of credit scoring. I think we built the first credit scoring model back in the 60s and using early versions of discriminant analysis. That was before logistic regression came along. The FICO score is pervasive, so chances are whenever you swipe a credit card and whenever you apply for a car loan, a mortgage, any other loan product, you get scored several times by FICO scores. And in fact, a large number of decisions are made every year alone in the US, and FICO score is available now in 25 plus countries and counting. And it amounts to about 10 million decisions per year, and that's about 4 times as much as McDonald's sells burgers every year. So just to get a sense of the amount of magnitude of decisions. And then obviously each of these decisions can be potentially life-changing for the consumer. If you get declined for a mortgage, how bad is that? Or if you have a low FICO score and you get a car loan, you're probably going to pay thousands of dollars more in interest rate than somebody with a higher FICO score. So it's very important to keep these models very transparent and explainable. And credit scoring is heavily regulated, so there are a number of laws against disparate impact and the right of people who are declined for credit. We need to be able to explain to them the reasons why they declined and such. So FICO score is used not just for origination, but everywhere in the life cycle of financial lending, which includes account management and collections. Hopefully not collections, but it does happen. And so that said, so just brief high-level explanation of what the FICO score is. It's a number between 300 and 850, the higher the better. And it's based on the information that exists about consumers in the credit bureau agencies like Experian, TransUnion, Equifax, the big ones. And basically, it's designed to rank order risk. So it's not designed to give you accurate forecast of PD, the probability of delinquency, because that depends also a lot on the economy, on the economic cycle, on the types of products, banks, design. So all that needs to be calibrated by the portfolio managers and keeping track of changes in consumer behavior and the economic cycle. Take that into account. But the FICO score itself is designed to be a very robust rank orderer of risk. And as such, it's rank ordering odds. So we cannot say for certain Gerald is going to default, but we can say people who look like Gerald have odds of 20 to 1 to pay back as expected. And in this little example, it shows you the situation, let's say at a FICO score 620, maybe 1 out of 4 people goes delinquent, and at the 640, it's 1 out of 7, and so on. And typically, the FICO score is scaled so that 20 points double the odds. As so often with statistical models, the score is linear in log odds, or odds are exponential in the score, to say it the other way around. So this is the anatomy of an overly simplistic illustration of a scorecard. So the FICO score is based on a technology called scorecards. To build a scorecard, you typically have a few predictive variables that are already categorical, like do you own a house or rent? That's categorical. But then there's a very large number of variables that are derived from the credit bureau information, from the credit records, like about your payment history, how many times in the last year or two have you experienced a late payment, for example, or did you have delinquency in the last year, and how many? And you can see for each of these variables, there is, we call them characteristics. Their ordinal ranges are binned into attribute ranges, and then each range of each attribute gets a points. And here you see that if you had some historic delinquency, the longer ago it happened, like if it happened more than 24 months ago, you get good points for that. But if it happened more recently, that's a bad sign, so you get fewer points. Obviously, if you never had a serious delinquency, you get the maximum points. So that's what you would expect, to see from a trained model. But it turns out ever so often there are certain things that don't quite make sense, or they're not fully intuitive. So, for example, outstanding debt, you see the higher percentage of utilization on your credit cards. Utilization basically means out of your credit card limit, how much of that limit do you use? Turns out that people who are close to maxed out tend to be worse risk. So typically people would expect a monotonic relationship across the ordinal range. But sometimes you see something weird, that maybe people at 40% utilization are suddenly a little bit better than people at 30%. And so there is a certain amount of engineering when we assign these score points. They are empirically derived, but subject to constraints on explainability. So we use certain types of nonlinear programming to optimize those score weights subject to constraints. And then there is obviously, there's virtually hundreds of these characteristics exist in characteristic libraries. They are all kind of domain expert derived characteristics. So each of these features, as we would call them in machine learning, is very explainable. The assignment of points to the features is very explainable. And then there is a characteristic selection algorithm that selects, let's say, from a characteristic library of 500 variables, may select 10 or 15 of them as characteristics into the scorecard. And then there is a whole science and art of binning, like how, if you make these attributes too narrow, you get a lot of noise. If you make them too wide, you're approximating a smooth function through a very high, granular stair function, and you're losing some signal there, so you have too much bias. So there's a good old bias variance trade-off in constructing these models really well. But what I want you to remember is this real simple model, easy to explain, and there is a certain amount of domain knowledge that goes in on top of the pulling most of the signal out of the data. So we combine learning from data with domain expertise and business constraints on explainability when we construct these models. Now, each single scorecard can model a nonlinear function. So sometimes we hear, oh, scorecards, kind of old technology, it's just linear modeling. But in reality, these things can be nonlinear step function of the ordinal ranges. And the experts of you will ask, yeah, but how does it capture interactions, right? Basically, the way it computes a score, it just adds up the bins or the attributes into which a consumer falls. So let's say this guy had a delinquency 30 months ago. From there, he gets 55 points, and overall utilization is 30%. From there, he gets 45 points, and then you just add that all up, and the sum of points is the FICO score. It's not quite as simple, because it turns out the population is very heterogeneous, and you can do better if you have several dedicated scorecards for different subsegments of the population. So that looks roughly like this. You have a full, let's say, the scoreable US population, let's say 150 million people, and then there may be a split into those who had historic delinquencies and those who were always very clean, and then underneath those may be another split. So you kind of have a binary tree structure, if you want, to create a partition of the full population into mutually exclusive and exhaustive segments. And then in each segment, there is a dedicated scorecard, and different scorecards in different segments can use different subsets of characteristics and different binnings. So it's a fairly sophisticated system. And you can show mathematically, when you write the formula down for the FICO score as a segmented scorecard, it captures interactions between all the variables that are used to define the splits in the tree and all the variables that are used in the scorecards as characteristics. So when I looked at the scheme, it's more than a dozen scorecards, and tree level 5, depth 5. It captures up to 5-way interactions. So despite it being simple to explain, it's a very sophisticated nonlinear model that captures interactions. As you can imagine, the development of this system is very tedious because there's multiple scorecards involved, a lot of score engineering. And the biggest problem of all is kind of to figure out what's a good segmentation, because there's a kind of an exponential search space how we could segment a population. And this differs in different countries. We just did a project for the UK, and there, again, we have a different segmentation from the US. And in other countries where consumer behavior is more different and the data sources look very different, the segmentations could be totally different. So kind of alone the segmentation analysis would demand to use more AI and machine learning to get a higher degree of productivity in the construction of these models. So that's why one of the reasons we are very interested in AI and machine learning. Another is obviously benchmarking, because you never quite know when you construct these models, do you leave predictive information on the table, right? And if you could move the needle a little bit, predict a little bit better, that could make a big difference. So I should have said, when we construct these scorecards, we use all kinds of machine learning, but probably without calling it machine learning. But characteristic selection is an automated process, is part of machine learning, or automated binning, interaction detection, stuff like that. We always use that. But as I said, we always balance this machine learning with the domain expertise to ensure the transparency, compliance with the regulation, and also to mitigate biases. And credit scoring data can be full of biases because you get this kind of selection bias that you can only observe performance of people who have gotten a loan in the past, but people who didn't get a loan in the past, kind of the rejects, you don't know, you don't have a label. So you need to be very careful about that as well. Nevertheless, the question is always, how does this compare? How does the FICO score compare about the latest and greatest machine learning algorithms? So you are all experts, so I will be very fast here. Basically, this is a typical ensemble type of model that combines the predictions from many classification and regression trees, card trees. Each card tree is a good old binary tree trained by recursive partitioning to optimize something like a separation between goods and bad payers. And then they're all combined into a prediction function called the score. And you can think basically of the score, it's just a regression approximation of that noisy point cloud, which is the input data set. So my short definition, my favorite definition of machine learning like this is basically, it takes data and turns it into an algorithm. So the algorithm is basically how you can compute a score based on knowing the values of the predictors. So this immensely complex model. Big difference between these models and the scorecard is that these models have 10,000s, if not 100,000s of parameters. And none of them has any meaning to anybody. So it's kind of completely sub-symbolic. It's not like regression coefficients where you know this is a slope or a sensitivity or elasticity. No, these parameters in those trees have no meaning. And we're using gradient boosting. So that's kind of a sequential method to train each tree on the residual of the previous tree. We use a lot of shrinkage to make sure we're not overfitting. But the end model is kind of a black box. There are many good algorithms for diagnosis of these black boxes, like basically simulating the input-output relationship to get a sense of, which features, if you change let's say the size of an input, the magnitude, how will the score change, and you plot these curves called partial dependence functions and all that. That is all great, but as I said earlier, we also need to be able to go into the model and put some constraints and make some tweaks to make this fully explainable. And this is today, with today's machine learning, not really what machine learning is designed for. Machine learning is really designed, fit the best function to the data. Don't mess, right? Human, keep out. And so this is for us kind of an ideal complement or benchmark. And the question was, how does this model perform compared to the FICO score? So what we found is that we got a mild performance improvement, less than 2% KS. KS, Kolmogorov-Smirnov statistic, basically a measure of the how far away the conditional score distributions for the goods and the bads can be pushed by the algorithm. So you want KS to be high. So a 2% improvement in our world is statistically significant, but it's not a killer improvement. So our customers, the bankers, typically say, we would only buy your next version FICO score if you can improve KS by at least 10 points or something. So 2 or 10%. 2% is not too much of a wow. Nevertheless, it's a good number, and we use both. We tried gradient boosting, as I said. We also used people from our fraud team who have a lot of experience with deep learning and neural nets. Got the best guy, built a neural net, and he kind of also leveled out at a similar level with the gradient boosting. So we kind of are very confident. These are kind of the best results we could get with machine learning. So this may have been a little frustrating and underwhelming for some of us because we had hoped to find a bigger improvement. But I think the reason is because that good old FICO score is already a very sophisticated model capturing nonlinearities and interactions. And frankly, it has been developed by generations of analysts and scientists over the last 20 years or so to find reasonably good segmentations. So it's always easy to show machine learning has great lift over very simplistic models, and that's a marketing tactic. But when you have a very good model built on, let's say, segmented logistic regression or something, it's much harder to get a lot of lift from machine learning. So that's kind of what we found. However, the really good news with this latest and greatest machine learning is productivity. So we were basically able in 1 week to get as much, if not a little bit more, predictive power squeezed out of the data than with a full-blown segmented scorecard development, which would take many people several months. So since we build these scoring models a lot in research, like to see, is it time to build a new FICO score, or there is a new data source, let's see if that gives some lift on margin to the existing model. We're constantly building kind of research FICO scores in the lab. So for us, having this machine learning is a great productivity boost to be able to say much quicker, oh, we think there is value in this new data source, or we think it's time to build a new FICO score, we see improvements. And so this has been a big success. I think also the other thing, had we tried to bring directly to the FICO score team the black box machine learning and say, wow, it's much more accurate, they would have not liked it because they wouldn't have quite related to the black box. But what I will show you next is how we blended the technologies and combined this time-proven, transparent scorecard technology with the latest machine learning stuff to create this kind of something that's much more acceptable in our market credit scoring for regulators, for users, for stakeholders, for other analysts and risk managers. And so this is kind of a way we brought more and newer machine learning into the FICO score research and development. So that's my next topic. But before I go there, I wanna tell you one more thing, and it's about these machine learning black boxes. So my colleague said, we need to do a test. We have a service, it's called myfico.com, where consumers can go and simulate scenarios. Basically, they can say, what will happen if I pay down my credit card debt? How will that change the FICO score? And so this is kind of a simple score simulator. And I think this person has $1,493 balance on their credit cards. And now they're simulating what will happen if I pay off 90% of my balances. And it's basically an axiom in the credit industry that if you pay down card balances, you become a better risk. And your score should only go up, if anything. So we put in this probe model, in this simulator, we put both first the FICO 9 and then a machine learning model to see under this simulated scenario what will happen to the simulated score. And so what happened was that for the FICO 9 score, because it was engineered to be explainable, out of those, and we ran this on like a large sample, maybe 10 million random consumers in the US, we ran this scenario. And none of them received a score drop as a result of paying down 90% of their credit card balances when we use the FICO 9 model, which is the latest FICO score. But with the stochastic gradient boosting model, 9% of the consumers under this pay down scenario experienced a drop in the score. It was a very slight drop, maybe only 2-3 points, but nevertheless, it's something that would certainly confuse consumers and the bankers and the regulators. They would all be kind of confounded by finding, oh, you pay down your card debt and your score drops. That's not good. So we'd be in massive trouble. And this goes back to yesterday, what the lady who had the background as a sociologist, and she talked about the ethics. And she said it's not only about accuracy. Accuracy doesn't help you, but your model, it needs to pass the common sense tests, right? And so the stochastic gradient boosting is a bit more accurate, but it doesn't pass the common sense tests. And so it wouldn't be a good model directly for the FICO score. But now I want to introduce this blended idea. How do we bring together these different technologies? So basically, it's a short pipeline, just very briefly, high level, go through the steps. First, we build the best possible black box machine learning model where we don't care about interoperability. This is easier said than done, and some speakers pointed that out. You have to do hyperparameter search and stuff, so we benefit a lot from parallel computing at that level. And then we diagnose the model, so we look at things, standard reports like variable importance, partial dependence functions, interactions. So you can, the beauty of this machine learning is especially gradient boosting. You can compare baseline additive models with models that capture low or higher order interactions and see and test for interactions and find ideas of variables that interact with other variables or interact with many other variables. And these tend to be good candidates for segmentation. So we gain a lot of information out of this machine learning thing. It can serve us as a benchmark, right? It's kind of the upper limit of predictive power that you can have if you don't care about interpretability. That's good to know, because we want to know when we introduce palatability constraints, how much predictive power may we give up. It's a trade-off, and we like to know where we operate on that trade-off. But then now this is kind of the really cool thing. So we basically score out the development data set with the best machine learning model and attach the development data set with the best machine learning score that we found. So initially the target is simply binary good, bad. You paid or you didn't pay your loan. But now we add another column to the data set that's the best machine learning model. So that's basically a distillation of everything we know about your degree of badness. So it's a number between, let's say, 0 and 1, a probability. And that has actually really distilled the information that's in that noisy binary good, bad label into a grading, so to say. And then we develop this TGAMT means transparent generalized additive model tree. Yet another acronym, not to be remembered, but basically it's a segmented scorecard tree. But instead of deciding these segmentations manually, we run a recursive algorithm that's similar to the CART, classification and regression tree algorithm, but it has scorecards in the segment. So basically it starts with a single scorecard at the top, at the root node for the full population that tries, and this is the other thing, it tries to predict the machine learning score. That's the key. We no longer try to predict the binary good bad target like in a logistic regression setup, but we try to predict the machine learning score in the least square sense. So it turns out this new target is a better target than the noisy binary 0, 0, 1 target. And so this is really mysterious. Why? I think it's because it filters out a lot of noise. So it allows this recursive tree algorithm to focus less on the noise and more on the signal that the machine learning model has found. But basically, going back to this recursive tree, so it starts with a single scorecard for the full population that tries to predict the machine learning model. Chances are the prediction won't be that great because that scorecard cannot capture a number of interactions that the machine learning model captures. And then the algorithm tries all kinds of splits using all the variables we have in our characteristics libraries to define possible splits into children branches. And it compares all these splits for which one is the best. And also, is the best split giving me any substantially better performance than that parent model? The answer is usually yes, because we have millions of records to train. So you can do better than a single scorecard. And then this same algorithm to find the optimal split and see whether optimal split is better than the parent is recursively done again and again until eventually either there is no more significant performance improvement with further splitting, or I run into some kind of minimum counts criterion, then it stops. And so this way, this segmented scorecard tree is built totally automated. And so there's massive, massive time saver here. And I should also say that the scorecards that are part of this segmented scorecard trees are also trained subject to the same palatability constraints that we insist on in the scorecards to be able to explain why did you receive more points than this guy? Oh, because you have lower depth ratio. So there's a lot about enforcing monotonicity. But not everything is monotonic. There are also some relationships that are like mountain-shaped or valley-shaped, like unimodal relationships where you have, first monotonic increasing over some range and then monotonic decreasing over some other range. So that's another thing. There's a lot of special values and missing values usually involved. Sometimes these also need to be constrained against each other or against ordinal ranges. There are certain problems with multicollinearity that can be fixed by constraints like weight sharing. If there are two different attributes from two different variables, but they have 99% overlap, that would lead to variance inflation if you don't do something like weight sharing, where you can say, I want these two attributes to receive the same score weight. So there's all kinds of palatability constraints so it's not strictly a maximum likelihood thing where I just estimate the score weights to get the best possible approximation of the target, but it's always subject to these palatability constraints. And that works always in this recursive search so that the end result is the best possible segmented scorecard system subject to palatability constraints. And then there's still a stage where before we would deploy that, the FICO score developers would go into each model at the leaves of the tree. Maybe there are 10 or 15 scorecards, and go kind of manually into each scorecard and make last little changes. And then usually it goes through a legal review. A company lawyer sits there and makes sure it doesn't look like discriminating against protected groups, and that whenever there is somebody declined for credit, it can be explained based on the patterns, and then we can deploy. So this way, in a way, very convoluted way, we make use of machine learning, A, as a benchmark, B, to give us ideas about what are the important variables, what are the important interactions, and then C, it creates this target score, again, the best score, which is kind of a better target. It has better statistical properties to develop this segmented tree than using the original target. So in this way, I think we make the most of the data, but without running the risk of delivering something that has some parts and areas that are difficult to explain or cannot be explained. So it's kind of trying to marry the best of both worlds here. And we recently used this approach to build a new FICO score for the UK. So it has made it out of the lab finally into the real world. And here, kind of some final comparisons. So compared the FICO score as a baseline, found less than 2% improvement in KS using stochastic gradient boosting. The neural net was a little less, but don't say Gerald said the neural net doesn't perform as well. It was, I guess, if we would have given that person more time and he had gained more familiarity with the data, he would probably also had, maxed out somewhere at 2%. But that's just kind of what we found. And then the explainable AIML, what I just showed you, was basically on par with the FICO 9 score. And interestingly, it found a very similar segmentation that the FICO 9 score uses without us telling it. So it was very reassuring that the generations of analysts didn't totally fail discovering the best segments. Machine learning has kind of verified that in a good way. So with that, I want to conclude that we find AI and machine learning especially attractive in the FICO scores team because of the efficiency gains. But we also found if you just use a data-driven algorithm, it can lack palatability where we need it. We always have to balance our knowledge about the operational requirements for something like a FICO score with the learnings from data. So it's a very balanced knowledge and data kind of development. And finally, I wanted to say, so you'll see these challenges are everywhere, probably in your work as well. Healthcare is certainly an area where you need, very high stakes healthcare decisions need to be very well reasoned. And you use AI more like augmented intelligence, right? Where you get ideas and recommendations from a computer, but the final decision and how to explain it to the patients needs to be made by a human expert. AI is not yet so far advanced that we could say, oh, forget about those human experts. And so I think it's a hot topic in research, explainable AI, that can be interesting for many, many applications. So thank you.
Hey, thank you, Gerald. Any questions? Does anyone have any questions? All right, we have one in the front here. Here you go.
Hi, that was a nice talk. Thank you very much. You mentioned monotonicity in your scorecards. I was wondering if you explored monotonicity in the neural networks and GBTs.
Yeah, great question. So since I mentioned monotonicity requirement and whether we explored monotonicity in trees and neural networks, no, we didn't. But I'm very aware of a few tools that are now becoming available, like monotonic trees, I think GB Boost or something. So this is certainly a promising direction. Yeah, thank you.
Any other questions? Two over here.
Thank you. Wondering about the time period in which you train the model and how you test it, if it's multiple tests and how that works.
So the time period over which we trained the machine learning model, and what was the second?
And then the testing, like those numbers that you showed, is that for 1 month of data, or is that
okay, and the testing, yes. Yeah. So for testing, we usually we do two things. We have a random holdout sample from the same time period, and also we test on an out-of-time sample, like maybe a year later. Typically, we don't want to go too far back in the past because we want to know, given today's consumer behavior, today's economic environment, how well does it work. But our time period for defining the credit performance is 2 years. So if somebody defaults on any one loan over the 2 years, we call that a bad. And otherwise, it's a good. And so that's kind of the answer.
So 2 questions. How can I get a score of 1,000? And also, how do you account for new products that banks put out in the market as it relates to like the utilization rate? Because what I found in using these products where they try to predict what the score may be is that, for example, you have people like myself who will actually go out and accrue tons of credit for rewards. So it says, okay, you pay your credit cards down, and then your score is going to skyrocket, right? But in reality, I'm paying my balance off every month. I may carry like a $7,000 balance per month. I pay it off every month, and my score doesn't increase at all. So there seems to be some bias related to delinquency versus the actual, or the targeted delinquency versus the actual reality of incentive. So how do you address that in your models?
So I'm not exactly sure about the bias, but you're saying, are you saying the model is not distinguishing between people who pay down the balance every month and people who don't? Or
right. So
yeah.
Right. So
okay. Yeah. So there's interesting. That's a question of the data source. So there is a type of data at the credit bureaus called trended data, where you can see the payments that people make every month towards paying down their credit card balances, which will take care of that. So it can distinguish between transactors and revolvers. Interestingly, it doesn't really move the needle on the predictive performance. Yeah. So I wouldn't call it a bias because, I mean, you know, it's a very deep topic to define even what's a bias. But what we need to make sure is that the results, we use all the data at hand, right, that are economical sensible by the bank to acquire, to make the best possible predictions, and then that the points are assigned in a fair way that's regulatory compliant. So that's what we do.
All right, one last question, and we have to move on.
I had a question regarding your machine learning models. Right now, your KS is not big enough to pursue doing them, so you're going to still stay with your scorecards. But as you keep getting better and your KS becomes something that you want to do, you already showed that productionalization, it's actually being decreased by the time it takes to do to the actual models. Is federal regulations always going to constrain you from pursuing that space, even if it makes your work more efficient by pursuing an ML model or AI model?
So I'm not sure if I understood the question
So
fully.
you were discussing the black box,
yes,
and how federal regulations is going to stop you from pursuing this because of the lack of explainability. Even if you show increases in efficiency by pursuing this space, would at the end of the day stop you? Federal regulations stop you from doing that?
That's a good question. So let's say if the regulations make it too hard to deploy the black boxes, and at the same time it means we're leaving some predictive power kind of on the table, right? How does that jive? And what happens if maybe in the future, maybe future machine learning could even improve the KS by 5%? So, I mean, the answer is that I think there is no easy answer. You always have to deal with a trade-off between, you know, on the one end, maximize accuracy, and then the other thing is subject to explainability constraints. And unfortunately, it tends to eat a little bit into the accuracy when you enforce the palatability. I think the good news is it's not eating much into the accuracy from our experience. Basically, there are zillions of models that all predict about equally well within a margin that may not be relevant for the business. But some of these models are much easier to explain and to defend to the lawyers than others. So the business will always go to those models that are much easier to defend. And I think FICO will always adapt to, you know, what does the market want, right? And what's the business? Is the business willing to take risks with black boxes? Well, we can do black boxes, right? But right now, I think our big bank clients, they all mortified to roll out a model that they can't 100% explain. So they are willing to give up 1 or 2 points in KS.
So this is a really hot topic. So are you going to be back here around with coffee for lunch? So if anyone has any more questions, Gerald will be here. Thank you so much. Another round of applause.
That was Gerald Fahner, Senior Principal Scientist at FICO, sharing how his team at FICO combines machine learning with modern segmentation scorecard technology and domain expertise to ascertain maximum predictive power of the FICO score while adhering to explainability and regulatory requirements. If you enjoyed that presentation, make sure to subscribe to our channel below. And if you want to see more content like this, look for a link to DSS Insider where you can watch content like this on your own time. Thanks!